For our next speaker is Kate Dennis from Piccaro.
Thanks very much, Carol, and also thank you to both USGS and CUAHSI for having both Piccaro and LGR here today. I think it's a unique opportunity to share a little bit about what we're thinking about and the technology and an overview of the applications. So luckily for me, I'm going to sort of skip through a number of these first slides very quickly because I think the audience is really aware of what stable isotopes in water can be used for. I have this very brief schematic here of the basic principle which drives all of this, and that's the idea that light isotopes will preferentially go into the vapor phase. Heavy isotopes, on the other hand, will condense out first. And you can use that basic relationship to start understanding many things throughout the hydrological cycle with isotopes of oxygen and hydrogen. Very quickly, just as a reminder, we all probably know this, but of course, what we're doing is we're measuring the isotopic composition of a sample water as compared to a standard. Most typically for water isotopes, we're looking at VSMO2. And of course, from delta O18 and delta D, we also have the ability to look at a secondary parameter, deuterium excess, which is basically the deviation from a global meteoric water line. And of course, as Elena mentioned, there is also this third isotope of oxygen, which is often forgotten about, but hopefully we're both bringing that back with a vengeance, is O17. And that's the least abundant stable isotope of oxygen. And what's so interesting about O17 is that we have the secondary parameter O17 excess, which again, Elena mentioned before. Sorry, I just realized I forgot to start my timer. This is something that I certainly, when I joined Piccaro, was very familiar with. This is an isotope ratio mass spectrometry lab. This is where I spent my days during my PhD and postdoc. And I got very excited when I started learning about these tiny instruments that could be placed on a bench and did very similar things to what IRMS were able to do. Of course, the other advantage of these laser techniques is that they're very field deployable. And they are also now on the same level of precision as isotope ratio mass spectrometry. So we're really changing the way that people can make isotope measurements on water, on CO2, on methane, N2O, so many different gas-based species. So I wanted to start out by giving some application examples. This is something that many of you are probably familiar with. The global network for isotopes and precipitation has been managed for many years by the IAEA, and it's really allowed us to start constructing what is known now as isoscapes, so the spatial variability in water isotopes and precipitation. What's so interesting about these for hydrologists is that they'll start telling you things about evaporation processes, about moisture recycling, about sources of groundwater, various different things that you can learn from oxygen and hydrogen isotopes. It's really based in the theory that was set back in the 60s by Harmon Craig with the global meteoric water line, this very well-known relationship between delta O18 and delta D, and using the secondary parameter to look at various processes that might be driving you away from this global meteoric water line. Similarly, Willie Dansgaard was the first one to really notice this relationship between the temperature in a local region and the isotopic composition of the precipitation in that region. And these are really what's driving the use of isotopes today. So moving forward through the talk, I'm going to give a few more example applications, then I'll jump into the technology of cavity ring-down spectroscopy, overview what we do at Piccaro to make these measurements. I'll talk about it by looking at water isotopes themselves, and I'll also mention some of the challenges associated with measuring water isotopes by laser techniques. I'll then spend a little bit of time talking about new directions for measuring water isotopes at Piccaro, and then finally I'll close, much like Elena did, with a brief overview of what else you might be able to do as an isotope hydrologist or a biogeochemist using Piccaro's instruments. So this is a really interesting effort, I think, that Gabe Bowen did at the University of Utah. As Superstorm Sandy came up the East Coast in late 2012, he sent out an email to IsoGeochem, to many other user groups, isogeochemists around the East Coast, and basically asked them to go out and sample the rainfall happening during that event. He's since then measured a huge number of these on his Piccaro analyzers, and we're starting to see patterns in the spatial variability of isotopes during an extreme weather event. Also, many other examples might deal with not only precipitation, but also vapor. So this is a study by Max Berkelhammer, who used to be in David Nune's group at Colorado. I believe he's now moved to Illinois. But the idea that you can combine atmospheric ambient water vapor measurements and liquid water measurements from precipitation or from leaf water or stem water to understand the balance of water in an ecosystem. In this case, it was a forest in Colorado, and they were able to use water isotopes to understand the significance of dewfall in this environment. And it was really something that would be very difficult to do with traditional techniques because you wouldn't be able to get the high-resolution vapor data that he was able to measure in this study. On a more conventional scale, this was a very recent paper that came out using a Picarro instrument in Costa Rica to basically measure the isotopes that were collected for the GNIP study. I believe it's between 1990 and 2005. And again, this sort of highlights how precipitation isotopes can really help us understand the various evaporative enrichment that might be occurring in some regions versus recycling in a forest ecosystem, in this case in the central highlands of Costa Rica. So again, there's types of things that you can start piecing together with isotopes. Another thing that we got very excited about was some work by Niels Mansgaard down in Australia, where he coupled a home-built diffusion sampler with his Piccaro L2130. And what that did is it enabled him to measure real-time liquid water changes by using a diffusive process. So basically, he's using a diffusion cell to equilibrate liquid water with dry ambient vapor around that, and then the instrument is used to measure that isotopic vapor and delivers high-performance real-time delta O18 and delta D. I'll come back to this a little later as well. And then finally, of course, as hydrologists, you're not only interested in the water itself, you're also interested in dissolved gases, in nitrates, many different nutrients, and so on. This is one example that has come out of Rob Jackson's lab at Duke University. It wasn't all done by cavity ringdown. It was also some conventional IRMS techniques, but it's just kind of showing what else you can do. What they were measuring was dissolved gas in drinking water wells, dissolved methane, propane, and ethane in drinking water wells close to drilling sites on the Marcellus Shale. Interestingly, they actually concluded from this study that they did think that the groundwater was contaminated by stray gas close to drilling rigs. There was another study that found the opposite. They didn't see any evidence for contamination. But these type of isotope tools are really interested in understanding groundwater contamination issues due to oil and gas activities. Okay. So moving on to the technology itself, cavity ring-down spectroscopy is also a laser-based absorption technique. This is a picture of our cavity itself. I was going to show it in scale to the people in the room, but it's about 30 centimeters long in total. The volume of the cavity is about 35 standard SCCM. Sorry, SCC, not SCCM. It's a three-mirrored cavity, so it's got a triangular configuration. The basics of it is that you shine a laser light into that cavity. It bounces around between those three mirrors, and you are measuring the ring down time, so the time that it takes for that laser light to decay. Obviously, that laser decay depends on what wavelength you're at and what gas is in that cell, because if you're at the wavelength of an absorption of, say, an H2O molecule, you will have that light will decay more quickly because of absorption by that H2O than if you're in a region that does not have absorption by H2O. So really what the main difference here is that we're measuring ring down time, not absorption. Again, I mentioned we have a small three-mirrored cavity, has a very long path length. When you're bouncing around that laser, you've got an effective path length of over 10 kilometers, even though it's very small in size. It's a time-based measurement, and you're switching off and on the laser, and you're scanning it across different wavelengths. The basics of the process go like this. The first thing you're going to do is you're going to select a wavelength using our patented wavelength monitor. You're then going to measure the decay time at that wavelength. And as I mentioned before, if you're right on the center of a peak, so if you're on the absorption of, say, H2O18, that ring down time will be very quick. So the light will decay in the cavity much more quickly than if you're in a region that you're not absorbing water. Likewise, if you have no gas in the cavity, the ring down time will be longer because there's nothing to absorb that gas. You calculate the loss at that particular wavelength, and then you're repeating this cycle over and over again. You can then calculate the gas concentration because it's proportional to the area under the curve, given constant temperature and pressure. And that constant temperature and pressure is very important. And the reason for that is that the absorption spectra of a different molecule will change slightly depending on the temperature and the pressure of the gas in that cell. And so because of that, we actively control and monitor both the temperature and pressure of the cavity. So our temperature control in all of our systems is plus or minus 0.002 degrees C, so we're talking on a millikelvin scale, and we're also very tightly controlling pressure. What that means is that even with ambient fluctuations in humidity, in temperature, you can have very low drift analyzers that require few calibrations. And so these analyzers are very stable over time because of that precise temperature and pressure control. Okay, so moving now on to how we've applied cavity ring-down spectroscopy to water isotopes themselves. I'm going to focus on two different analyzers today, the L2130 and the L2140. The L2130 is our most popular analyzer. It measures delta O18 and delta D to extremely high precision. The L2140 was our analyzer that we released last summer. And it also has the capability to measure not only delta O18 and delta D, but also all three isotopes of oxygen, so you can measure delta O17 and O17 excess. The analyzer itself is just, I realize I don't think I've had a scale yet on here, so it's about 8 inches high by about 1.5 feet in both width and depth. So you're looking at something that's really a benchtop item, but of course the analyzer on its own is not enough. You need to also have front-end peripheral devices to be able to utilize that for your isotope work. The main thing I will focus on today is our high-precision vaporizer, and that's really just a decision I made based on the audience. Most of you are going to be isotope hydrologists, I believe, and therefore are going to be interested in liquid waters. But you also may want to be, we have a lot of atmospheric scientists we work with who measure ambient water vapor, and they might want a standard delivery module, for example, to calibrate the system for ambient vapor measurements. And I will touch on a few other peripheries as well. So before I do that, I just very quickly wanted to bring up the specifications of the L2130. I'm not going to go through all of these numbers, but I believe this is being recorded, so you can always pause and look at this later. But the main thing I wanted to note is that for liquids, you're looking at a precision on delta O18 of 0.025 per mil and 0.1 per mil. That is comparable with the best isotope ratio techniques out there, RMS techniques out there as well. And the other great thing about the system is that you can measure continuously water vapor, and also you can measure matrix-bound water using our induction module front end, which I'll review in a minute as well. The other instrument that we have is the L2140. I was going to do an overview of why O17 excess, but I'm going to skip over this because Elena has already covered this, including the exact same figure I was going to show. It's a great figure, and it's really helpful in understanding what O17 excess brings to the table for isotope hydrologists. If you want to learn more about O17, I highly recommend reading Boas's paper on this topic. It's certainly a very useful source in understanding this. Needless to say, the take-home message, though, is that because you're looking at this anomaly from the global meteoric water line, to make O17 measurements useful, they have to be done at extremely high precision. Making a 0.05 per mil measurement on O17, you might as well take your delta O18 and divide by 2. You're not going to get much value out of it. But if you can start pushing the envelope and getting to 10 per meg precision, so 0.01 per mil, you can start learning process level effects on that water or that water vapor. A few examples of what you can do with O17 excess. I'm not going to go through these in details, but just to get a sense of what you might be able to do. I think the other thing that I always like to mention at the moment is that, to be honest, I don't think we really know quite the scale of how useful O17 excess will be. There's been so few measurements made so far because it's a very difficult measurement to make with isotope ratio mass spectrometry that the field is relatively young. So I think, we've had 40 years to measure deuterium excess. We've only had a few years to measure O17 excess. So I think there's a lot to be learned here. So for our L2140, here are our specifications. Again, the take-home here is that we do guarantee precision on both O17 excess in addition to delta O18 and delta D. Our guaranteed precision on liquid injections is 15 per meg. I'll show some data where we do actually typically see better than that, but that is our guaranteed specification. And also I wanted to point out here that with the vapor measurement, we also guarantee this 15 per meg precision, and it's highly stable. We guarantee that over an hour-long measurement, so 3,600 seconds. And that, I think, is a real virtue of this instrument. It's highly stable through time, so again, it means fewer calibrations, but yet you can still achieve these high-precision results. So some example data here from the L2140. This is in a paper that is currently under review or in discussion at Atmospheric Measurement Techniques. It's been written with our colleague or collaborator up at the University of Washington, Eric Steig, also Vasilius Ginkins from University of Copenhagen. Basically, these few figures here show what the instrument does over 48 plus hours. Actually, it's 60 hours, my mistake. So this is basically what I did in the lab was I just lined up about 40 vials of the exact same water, and I just measured it for a long period of time. So I was taking 10 injections from each vial, moving through, and I didn't do a single calibration through that process. So the idea, and I didn't exclude any injections either. This is literally just every injection on there, and what do you see for your precision? For O17 excess, you're down at 7.7 per meg over that 60-hour period. So it's an incredibly stable instrument. Similarly, if you've got two samples and you're running them back to back, this is just two vials of different waters that I'm switching back and forth. Again, 10 injections from each vial. I threw away the first 3 injections for memory, which I'll get to in a minute what I mean by that. But again, no calibration, incredibly stable instrument through this period of time. The errors reported here are the 1 sigma on the average from each of the vials. It's not a standard error, so I'm not dividing by the square root of n here. This is just simply the 1 sigma on those average measurements. So configuration examples. As I mentioned before, of course, an analyzer on its own is no use. You need to configure it for your particular application. I will run through a couple of these different configurations, but the idea is dependent on what your application of interest is. There are different ways to set up this system and calibrate it. So the high-precision vaporizer and Autosampler. This, as I said, is going to be the most relevant for isotope hydrologists. It's a very simple concept. Basically, CRDS is measuring a gas phase species. If you're working with liquid water, precipitation, groundwater, river water, you need to convert that to vapor. So it's a very simple vaporization process, and then you then introduce that water into the analyzer. Each injection is about 2 microliters. We typically recommend 6 injections, but it depends how you're dealing with memory. So you're looking at using about 20 microliters per sample. Quick note on salinity. This vaporizer, it is possible to use it up to about 200 grams per liter. Saying that, any vaporizer, because the process is vaporization, if you've got high dissolved solids, you will have a buildup of material in that vaporizer, which can lead to enhanced memory and will require more cleaning. So it's not to say you can run saline samples forever and ever and never see a degradation in the precision of in the memory or performance of the vaporizer, but it can be done if done appropriately. Also requires a zero air source, so just if you're thinking about setting this up in the lab, you can either get a dry nitrogen tank or a zero air tank. Likewise, if you wanted to set it up in a field, a dry-right column also does the trick nicely. And of course, we've got an Autosampler, so this can run unattended. What I like as well is that the Autosampler is controlled by onboard software, so you can actually, I often go home over the weekend leaving something running at Piccaro and log in online and make sure everything's going okay, or if I want to restart something, I can do that and I don't have to go into the office, which is always a bonus. Standard deliveries module. So this is important for if you're doing unattended field field campaigns for vapor measurements. So atmospheric scientists like to use this a lot. It enables the introduction of 2 isotope standards at different concentrations so that you can correct for both your isotopic composition, so your delta value, but you can also correct for concentration dependence in your delta value. I won't go into more detail than that for now. Micro-combustion module, I will touch on this again in a minute. This is a very important addition to our vaporizer that allows you to be less concerned with organic interferences from contaminated waters. So, for example, plant waters, which are known to have alcohols, ethanol, methanol, they can interfere with the spectroscopy for any laser-based technique. The micro-combustion module is a way of dealing with that, and I will talk about this a little bit more in a few slides. The induction module, so this is a front-end system that allows you to extract matrix-bound water from a solid sample. We've used it for leaves, we've used it for stems, we've used it for liquids that have very high dissolved solids, things like juices. And it is a non-automated but yet effective way to measure matrix-bound water without having to do cryogenic distillation on a vacuum line. So we are quite happy with this system. It's not to say it can be used for absolutely everything. You do have to do methods development to make sure it's working well and extracting all the water out of your sample type, but it's certainly a tool that can substitute for cryogenic distillation if you don't have access to a vacuum line. And finally, ChemCorrect. So this is a software that's included with all of our L2130 analyzers. It will flag and identify those samples that we suspect could be compromised by organic interference, so spectroscopic interference. And it will do that right out of, if you import the data file that comes out of the system, you can run it through ChemCorrect, and it will tell you which samples it thinks are good to go and which ones that perhaps you need to go back, consider another cleaning method, consider a distillation method, or perhaps it's not going to be suitable for cavity ring down. Just a very quick note, of course, we do like to provide everything that you need to be able to measure water isotopes, so it's not just the analyzers. So, of course, we do provide consumables as well, so you can hit the ground running if you want to use these instruments in your lab. Manufacturing and testing at Piccaro. I just want to make a note that we do test all of our instruments before we ship them. We test them for precision, drift, memory, thermal stability, robustness, and a few more things. If you go to our website, you can see what we call the drop test. These are the types of things that just guarantee that our analyzers will be operational out in the field, so that you don't need to worry about taking it out to the Antarctic or wherever you may want to go. It will operate out in the field as well. Okay, so challenges and tips for users. I wanted to take a bit of time to just throw up here what we know are challenges to any lab making an isotope measurement on water. This is not specific to CRDS. It's not even specific to laser techniques. It does affect every way you want to measure isotopes in water. I'm just going to focus on the first two, memory and spectral interferences. I think that Len and Kai may talk about the other three, but I'm not sure for definite. But there are certainly resources online about that as well. So there are other things to look at to deal with calibration, storing of standards, and syringe lifetime. So memory effect. What is the memory effect? This is something I always like to talk to people, especially as they're first getting into the game of measuring water isotopes, because if you overlook it, it can be problematic and it will compromise your accuracy. You may have precise measurements, you won't have accurate measurements. And the idea here is that isotopic memory is the fact that the dependence of the next sample that you're measuring, the next sample that you're measuring will have a dependence on the previous sample you measured. And therefore, when you're running a CRDS or an off-axis ICOS instrument, you do have to inject water multiple times to get the isotopic composition to stabilize. There are different ways to deal with memory. It is dependent on the instrument design. Sorry, the ways to deal with it are not dependent on the instrument design. The size of the memory effect is often dependent on the instrument design. It's also dependent on the isotopic difference between two adjacent samples. The larger the difference, the more the memory effect you'll notice. There are two common approaches to dealing with this. We typically recommend that you do at least 6 injections per sample, and you ignore the first 3. You average the remaining. This will, though, depend on how isotopically different 2 samples are, and there are also different ways to deal with memory. For example, Robert Van Gelden and his colleague have actually mathematically accounted and corrected for memory. LIMS for lasers also corrects for memory. So there are different ways to quantify memory and correct for it so that you don't have to do multiple injections. What's nice about our analyzers is, as I said, we do test for memory before we ship them, and we guarantee that our instruments will arrive at 98 or 99% of the final value, dependent on the isotope, for any set of injections. Obviously, though, 98% might not be good enough if you've got a 200 per mil difference in your delta D. That might not be good enough precision for what you're looking for. So you may need to do more of that. But certainly in a percent value, that's what we guarantee. Just as a quick example, this is a test that we did. I believe this was actually done with some of Len's samples that he sent to us a while back, probably almost a year ago now. But this is where we went between 3 different standards of known isotopic composition in delta O18. And what you see here is that you're varying from about -55 per mil to approximately flat isotopic composition up to 0 per mil, and then back to a mid-range composition. You'll see that you can notice that dependent on the injection number, you will see a slight trend in that isotopic composition. You can also quantify the memory. So this is simply a calculation that looks at the difference between what you measure between a current sample and a previous one compared to what you expect that difference to be. And you'll notice that, as we said, by the 4th injection, you should be at 99% of the true value. You'll also notice that for the 3rd water type here on the memory scale, there's actually a lot of scatter here. And what this actually means is that memory isn't winning, precision is winning. So what I mean by that is that you've overcome the memory effect, so there's some noise in the measurement that's not related to memory. Okay, so tips for achieving accurate results. I'd say the most important thing is don't ignore memory. It's something that you need to be aware of if you're running this instrument. And you should, I certainly think either you want to do multiple injections and ignore the first few, or you should correct for that memory effect. So when you're dealing with that, think about designing your run with memory in mind. What I mean by that is don't put slap next to SMO unless you're trying to look at the memory effect. Stage them out. So put something that's -20 per mil you think, and something that's -15 per mil, rather than something that's 20 and -50. So just you'll have some expectation on what the isotopic composition of your water is, and design your run with that in mind. Other thing, of course, is calibration is obviously important. We do have very stable instruments, but of course I do recommend calibrating with known isotopic standards at the beginning of each run. You can also consider a bracketed normalization where you run standards at the end. And if you don't do a bracketed normalization, I would certainly suggest running a drift sample at the beginning and the end of your run, so that you can monitor how the isotopic composition, if the instrument is drifting through time with that run. Okay, challenge number 2, spectral interferences. As Elena mentioned, all optical techniques are impacted by spectral interferences. This is an example here of how a baseline spectra, how a spectra can change due to interferences. So for example, you can have an elevated baseline. So here on this figure on the right, you've got a clean sample versus a contaminated sample. Also, you can have additional features on that spectra. So for example, you can actually have additional distinct peaks in your spectra as well due to interfering molecules like methanol, like ethanol. So this was first pointed out, I think Willy Brand wrote about it actually just before Adam West did, but we started learning about the effect of spectral interference quite early on in the sort of commercialization of laser-based techniques. So there was a study done by Adam West when he was in Todd Dawson's lab where they compared conventional IRMS results with results from both an LGR and a Piccaro instrument, and they found that for various different plant waters, there could be large anomalies in the reported delta O18 and delta D value for those waters. And so we all started putting our heads together and figuring out, okay, how do we deal with this so that as a user, you don't need to be concerned that your sample might have an alcohol in it, and therefore that your isotopic values may not be representative of their true value. We have a two-pronged approach for this, chem-correct and the microcombustion module. I'm going to focus on the microcombustion module here today. As I mentioned earlier on, this is a online addition to your standard vaporizer, where you not only vaporize the water, but then you then pass that water vapor through a combustion module. There's a catalyst. You're using a combustive process, so it's not pyrolysis. It was initially, when we launched this, a pyrolysis process. It's now a combustion process, so you need to have zero air. And you're converting whatever that alcohol is to CO2 and water. Now, you are converting it to water, so this is not something that can be done if you're 80% ethanol. But if you have trace amounts of ethanol or methanol or other plant compounds, you can use this to actually remove that isotopic interference. So just some examples of what a spectral would look like with the MCM off versus on, and likewise what happens if you run a clean sample versus a contaminated sample using the MCM. So you'll see that with the MCM on, your baseline features are consistent between your clean and contaminated sample. Just to demonstrate that it is actually doing something, so what we do is we test all of our MCMs before shipping with simulated plant water solutions. So it's a mixture of ethanol, methanol, I believe it's got prenols in there. Anyway, so it's a compound. It's a solution that we mix to approximate what we think a plant water solution would be, and we then compare to running with the MCM on compared to the MCM off. We notice here that dependent on the alcohol concentration, if you have an MCM off, you'll have huge deviations in delta O18 and delta D. If you have the MCM on, you basically see no change in your delta O18. You will see a slight overcorrection for delta D related to that water that's being introduced, but it's significantly improved over not having an MCM. Okay, so just to finish up, I wanted to touch again briefly on the L2140. I just wanted to show you one experiment that we did that I thought was very interesting with this new instrument, and I'll also talk about the continuous water sampler for real-time monitoring of liquid water. This is something that's under development at the moment. It is not a released product at this time. So, real-life test on our L2140 for O17XS. One of the first things I did was I ran an evaporation experiment. I was actually trying to drive evaporation and fractionation in my sample vials as compared to usual when you're trying to prevent fractionation in your sample vials. So what I did is I left all the vials of water uncapped. I was using 250 microliter inserts, so I had small volumes of water. They were left uncapped to drive evaporation over a 40-vial process, so it was about 3 days with the number of injections I was running. And I had an expectation for that, and that was that my delta O18 would increase because of evaporation of the light stable isotope out of the water, and that my O17XS would decrease over that time. This is the result of that experiment. So here you have a plot of delta O18 versus delta O17 in the lower left-hand figure, and you will see that you are evolving along a line with a slope of 0.523, which is less than that equilibrium slope that was the global meteoric water line of 0.528. This would be our expectation for evaporation. And likewise, on the top plot here, you see O17XS decreasing as delta O18 increases. So I was really excited when I saw this because it's real-time demonstration of O17XS in the works. This is not something that could be easily done with IRMS because you don't have the ability to do these continuous measurements. You'd have to do more discrete samples, and it would be much more time-consuming. So finally, just to wrap up on the water, I wanted to show our continuous water sampler that we've been working on. This is, I mentioned at the very beginning, Niels Munsgaard developed this diffusion sampler. And this we've now taken a step further, done some tight temperature control, flow rate control, and we're able to measure water isotopes continuously with many different applications. To demonstrate it, what we did just in our R&D lab down at Santa Clara, we just hooked up the diffusion sampler to a running tap for a week. So it's a little wasteful on water. Pretty sure people wouldn't appreciate that now, but it did show some interesting trends. So the data here, what you're seeing here is along the x-axis about 7 days worth of measurements, continuous measurements, real-time data at about 1 hertz cycle rate, so about 64,000 data points. You will notice this is the deuterium, and you'll notice you get these spikes up to 0 and back down to about -110. These are our calibration points, so it's automatically switching between calibration standards, one that's about VSMO, one that's our local deionized water. And then interspersed with that is a real-time measurement of the tap water evolution. We were really surprised when we saw this. We thought it was much more variable in isotopic composition than we expected our tap water to be. And you could see some really interesting features, like over here between, I guess it's about hour 130 and 140, you see a rapid decrease in the isotopic composition over about a period of an hour. So you're able to capture very short time horizon events with this diffusion sampler. This is it plotted out versus delta 018 as well, so this is our sort of a local tap water, meteoric water line, if that's what you want to call it. The other thing that's kind of interesting, if you look at Santa Clara County's source water supplies, the Hetch Hetchy Reservoir has an isotopic composition of about -90 to 95 in delta D, and so what we think might be happening is that when you see these depletions in the isotopic composition of tap water, that's actually starting to bring in Hetch Hetchy Reservoir water into the municipal water supply. So kind of an interesting study. Obviously, this could be expanded out to many other things, river water, estuarine interactions, and so on. So this is something we're actively working on at the moment and pretty excited about going forward. Okay, so just to wrap up, Piccaro, I've only focused on water here. Obviously, Piccaro does a lot more than just water. We have many different concentration analyzers along with many different isotope analyzers at different measurement speeds. We have a fast analyzer for eddy covariance measurements and so on. We deal mostly with, at the moment, mostly with environmental scientists measuring things like CO2, methane, water, vapor. We also have a new analyzer that can measure N2O, ammonia, methane, water, and CO2, which is great for soil studies. And then we also do some analyzers that are more industrial scale processes, things like peroxide, HF, ammonia. And then, of course, we've got our isotope analyzers. For hydrologists, one instrument that you might be interested in is our 2201I, which is our dual carbon instrument. It measures delta C13 and CO2 and methane. And what's so nice about this instrument is it can couple with many different front ends to measure a number of things, for example, DIC and DOC. It can couple with a Costa Rica EA for bulk materials, delta C13, Combustion Module. It can be used with a closed system recirculation kit for soil studies. It can be used to introduce small samples. So many different applications here. And just to finish off, I wanted to show you this one, which is actually by some colleagues here at USGS. My colleague, Nabil Saad, works a lot with Randall Thomas up here, and forgive me if he's here, I've never met him. So, but they have a Piccaro instrument and an Aurora DOC front end so that they can measure DOC and DIC. In this case, I believe they are doing it for brines. So that's another application that may be interesting to isotope hydrologists and biogeochemists. With that, I will finish up and open the floor to any questions that you may have.